We're going to get started with the next presentation, image sensor and display connectivity disruption, Mr. Grant Jennings. And Grant is Senior Strategic Planning Engineer for Lattice, focused on identifying new ways to drive adoption of programmable technologies through next generation solutions based on leading connectivity and interface standards. He has more than a decade of experience in FPGA design, ASIC prototyping, and system architecture. He received his bachelor's degree in electronic engineering from Iowa State and his MBA from Texas A&M. Go Aggies. Grant Jennings.
Thank you. Hey, so thanks for letting me speak today. Appreciate the opportunity. So what I'm going to talk about is really connectivity disruption with image sensors and displays, and kind of the unique perspective that I've seen over the past 5 years through the MIPI Alliance, the evolution of CSI2 and DSI, and some of the unique mobile influenced use cases that have resulted from our devices because we have programmable devices that can be used in a variety of different ways. So the agenda, I'm really just going to give a high-level overview of kind of this evolution of as we trended to smartphones and now new use cases coming and leveraging mobile displays and cameras, application processors for new use cases, and the problems associated with that as you get outside of the realm of smartphones and tablets into new use cases. And then I'll go into a variety, the most exciting thing I think out of this presentation is I've got a ton of use cases that I want to go through and really go deep in some of the system level issues that you run into when you start to get outside of the range of what has been put on the shelf for you, so to speak, in terms of SoC development or module development. And then finally, we'll talk a little bit about how programmability doesn't just, and programmable bridging doesn't just band-aid use cases, but it generates a whole new variety of use cases that one can do outside of what was originally intended or originally thought of as development cycles go through. And then I'll just talk a little bit about future considerations for bridging and programmability. So this is just a high-level overview of kind of the latest trend as we have all of these displays, cameras that have come up over the last 5 years and have had critical needs in terms of cost, power, and size, and really focused on 2 to 5 cameras and 1 to 2 displays. And now as the smartphone market starts to kind of level out, there's all these other use cases that started to be generated utilizing the mobile technology for other use cases. And so while the volumes, volumes are still high on smartphones and tablets, one designer is going to focus on whatever is the biggest market, but also wants to identify the next latest trends. So how does a designer design with a smartphone or tablet focus, but then also be able to target anything from a wearable to a VR headset to an ADAS system or a drone or 360 camera? How can they focus in one area but then be broadly applicable to so many other applications? And so the first problem is it's difficult to find a device with the right interfaces to accommodate all these applications and ideas, right? If you're going to design an SoC, you want to target whatever's going to give you the biggest revenue, but that limits you in terms of if you need more interfaces for a particular design, you're limited. If you need fewer, you have a different cost profile, and also power becomes a concern as well. So this is just a breakdown of kind of just kind of bucketing the types of interfaces and how they're organized and how they're set up. So there's kind of three categories of interfaces as at least we see it. You have your kind of legacy CMOS interfaces, typically fairly slow speed, 150 megahertz CMOS bus, maybe up to 300. You've got proprietary interfaces in there. You've got MCU focused interfaces, some custom interfaces with wider buses, but it's all really centered around CMOS I/O, 1.8 volt, 3.3 volt I/O. And believe it or not, even though we've come a long way from that, there's still a ton of use cases and there's still a ton of equipment using that. And at the end of the day, sometimes just being able to connect to a simple CMOS interface that you can probe all the signals with a low-speed scope is really, really valuable and really allows you to get a very fast time to market on a solution. So still a ton of value there, even though bandwidth requirements have kind of shed away from it. Next one is source synchronous. So source synchronous, typically you have a clock lane and then multiple data lanes. And you have, this is where CSI2, DSI, DPHY, sub-LVDS, HiSPI, some other proprietary standards start to come into play. And this really starts to focus on power and performance for embedded systems. Then the last category is embedded clock systems, where you may have to, basically the system's set up so that the clock is embedded in the data, and there's some advantages and disadvantages to that as well. So basically you have, just within each of these buckets, there's even more interfaces outside of this, or standards, or proprietary standards, and it's difficult to find the future knowledge as well as the legacy knowledge and the IPs to integrate into your system to accommodate everything that you want to do. Okay, so now I'm going to go into enabling innovation through bridging. So, and we'll talk about some of the challenges and what an interface bridge is used for, and some of the examples of bridging use cases that one might want to use. So this is the basic problem statement for bridging. So basic problem statement for bridging is whenever the interface does not match between a camera and a processor, you need a bridge to convert that interface. Or whenever the interface between a processor and a display does not match, you need a bridge to convert those interfaces. Similarly, if the number of interfaces coming into a device doesn't match the number of interfaces that a processor has, you need a bridge to aggregate all those interfaces into one or two interfaces. And lastly, if you do not have enough ports on a processor compared to what's needed or required for the display, you may need to split or bandwidth reduce with a bridge to get enough interfaces for that type of display. So these are the kind of problems that bridging solves, and there's kind of three categories of problems that you may use a bridge for, and they're kind of different. So resolving unforeseen issues. This is kind of the, oh shoot, I have this AP, I've got all my code put into my processor, and I find out the customer wants to use this other display and it uses 2 ports, and I don't know what to do, so I have to throw in a bridge to accommodate that. And some of those common cases might be very common in the industry. As we went from CMOS interfaces to CSI2 and DSI interfaces, it was very common to go from CMOS to DSI and CSI2. As we go into other interfaces, there will be some common trends, and that's kind of the first need. Second one is just enabling backwards compatibility. So if you're developing a new platform, it's very difficult in the ecosystem. You likely hear conversations about this going on today about, should I adopt C-Fi or should I adopt should I adopt C-Fi or should I adopt D-Fi, or things like that. And those trade-offs all cost dollars, and so you may support both, but then there's a cost impact to that, and there's a power impact. And so that's kind of the other case, is that really you want to use bridging to make you feel more comfortable moving to the next capability, whatever's newest. You want to feel comfortable moving to the next interface standard and feel comfortable that there's a bridge to support your legacy customers or customers that have other needs. And then the last one is just solving new problems. So doing things that you didn't think were possible or were not foreseen until 6 months ago or something like that. And I think that one I'm going to just let the use cases kind of speak to themselves. But that's kind of the third one, is new enablement of new cases that were not foreseen. Okay, so now I'm going to walk through a variety of use cases. And the first one is a multi-CSI2 to single CSI2 camera aggregator bridge. So this may seem like something that would be very simple. You could just, you could manufacture a bridge like this, but how many sensors are you going to have on this thing? Are you going to have 2? Are you going to have 4? Are you going to have 8? Are you going to have 16? Okay, that has an I/O impact, so that has a cost impact. Are you going to merge them all with virtual channels, or are you going to merge them into one single frame? Okay, there's different things that you have to worry about in both of those scenarios. Also, if you get above 2 image sensors, you're probably going to have an I2C slave address problem, because most image sensors only have 1 or 2 slave addresses. And once you go beyond that, you need a multi-I2C or I2C master to multi-I2C slave bridge included to do this use case. So ideally, you have that integrated into the same bridge, so you solve 2 problems in one. If you're going to do multi-frame aggregation, so you're going to take all these image sensors, the frame from each image sensor, you're going to combine it into one CSI2 output, one frame, well, then the frames between each image sensor need to be synchronized. And fortunately, most image sensors have some sort of synchronization. However, they all need to be synced very close together unless you want a frame buffer or something like that. And also, if they don't share the same reference clock and you're going to combine frames, you could have drift between the image sensors over time. So you either need to resynchronize them or you need to share the clock. So these are just some of the things that come up that makes a standard, just choosing either to integrate it, you're going to have a cost and power delta, and this may not be a super broad use case, or it may be huge, but you don't know until you get a product out. And then also, some of the challenges that could come up and be unique for each and every customer that you run into. Okay, so here's another bridge. So this is just a proprietary interface to MIPI CSI2. So customer wants to use a higher end image sensor and wants to convert that to MIPI CSI2 to take advantages of some of the innovation with a mobile processor and a mobile influence system. So similar problems. This image sensor may have SPI for programming, and the processor has I2C or just wants the bridge to handle it. So you need an I2C master to SPI slave conversion. Some of these sensors are only work in a slave mode, so you have to control the readout of the image sensor. So you may need some readout control. Let's see what else. You may have a bandwidth aggregation, so the number of lanes coming in may be different than the number of lanes going out, and so you need to do some clock conversion and cross-clock FIFOing to get that data serialized on a lower number of lanes. And lastly, a lot of these proprietary sensors deserialized based on pixels. Whereas MIPI CSI2 typically serializes based on bytes or 16-bit words, depending on the interface. So you may have a pixel to byte conversion depending on how you're doing it or what you want to do inside the bridge, and that has some trade-offs that need to be considered. Okay, so I'm going to go a little bit faster here. So low-speed peripheral interfacing. So this is kind of a unique one where you have a CSI2 image sensor, and you're using a lower-end processor, like maybe even a microprocessor, and you actually want to do some processing in the bridge. Like you want to do some object detection that just works on light intensities or something like that. You may want to use a microcontroller to power a higher-end MIPI DSI display, and so you may need to store frame data and have some display controller and graphics processing capabilities within the bridge. You may also want to convert from MIPI DSI on an application processor or some microprocessors to CMOS, and this CMOS interface may be something very common, like a DPI, DBI type interface, or it could be something very special, like a specialty display, particularly e-readers. They have very unique display interfacing requirements, and so you need something that's very flexible to accommodate special needs of proprietary displays for certain applications. Okay, splitters and bandwidth reducers. So this can go into a wide variety of use cases, but converting MIPI DSI to CSI2 and MIPI DSI to DSI. So sometimes you've got a specialty image processor that you've taken from a system. For example, you've taken a system from an action camera, and it has, very unique code that maybe this vendor isn't going to give you the code or something like that. And so you just want to, you don't care about cost so much as the quality of the capability. So you've got this image processing system, it's got MIPI DSI out, and so you want to run that to your AP to do some other stuff based on the video data, but then you also want to show that on a display. Another one is MIPI DSI to dual MIPI DSI, and this is cases where you either have one high-resolution tablet that requires 2 ports, or you want to drive 2 displays, so kind of like a VR application or something like that. So you may only have 1 port on the AP, on the application processor, or you may have 2 ports, but one is used for some other purpose. One of the common examples as HDMI started to, there started to be some cost reduction in the application processors around HDMI. Some customers still wanted HDMI, so they used a bridge, a MIPI DSI to HDMI bridge for using 1 port, but then they also needed to drive a high bandwidth display on like a feature phone. And so they need camera aggregation and they need an HDMI bridge. And then this last one, CSI2 to CSI2 plus display. Let's see, I think that's similar to the other one, so I'm going to skip that one. Okay, repeaters. So this is a really unique use case that I think gets a lot of people thinking. Why would anyone want to convert MIPI DSI with the same number of lanes to MIPI DSI with the same number of lanes? So one reason is display replacement. So one of the most common reasons why phones have to be repaired is the display breaks. And so all of the replacement displays are typically not the OEM display. And so they have different commands to program the new display. So how can you hook a display that wasn't really intended for that phone up and use it as a replacement display? Well, you can put the commands in the bridge, MIPI DS or DCS commands, you can put those in the bridge, program the new display, and then pass through the video data. And you may need to do some cropping or scaling to align the new display and the old display, but those are things that are all use cases of things that people need, and that actually is a pretty high volume case. This last one, CSI2 to CSI2. Actually, before I go on that one, there's other reasons here too. Just as a redriver, cropping, scaling, those kind of things are common things around people that either want to go distance or have some need to not reprogram the code in the application processor. Okay, the last one, CSI2 to CSI2, so same question, why would you want to do that? So there's a lot of reasons. One, you may just, the camera may not be capable of doing raw to YUV conversion, so you may want to do that, and the application processor, for whatever reason, may not be able to handle it, don't want to reprogram the code, doesn't have the capability. Again, cropping, scaling, you may want to reduce some of the black pixels around the side, or you may have packet repair. So you may have a frame end packet that has some issue, and your application processor requires that, or maybe the image sensor doesn't send a frame start and frame end packet, and your application processor requires it. So you can add those extra packetization within the bridge. And then again, continuous clock. So MIPI CSI2 has a non-continuous clock. Some processors can't handle a non-continuous clock. So you may need to just take a system with a non-continuous clock and convert it to a continuous clock for that application processor. Okay, so that was some use cases. I have many more. I could talk for days on use cases. Come find me if you have use cases or scenarios that you want to discuss after the presentation. I'd be happy to go through them. The next part is really how programmability can aid in assisting this innovation of these types of use cases and more. So as we kind of seen, I didn't even go into some of the permutations of bits per pixel, types of pixel content, number of PHYs we talked a little bit about, compression, other interfaces, peripheral interfaces and high-speed interfaces, needs for virtual channels, some encoding. There's thousands of permutations here, and there's never going to be a one-size-fits-all solution. Because you also have on top of that the requirements of cost, power, performance, and size, which are unique to your application. So it's not cost effective to come up with a singular device to do all these use cases, a bridge IC for that. So what happens is, this is the challenge, it's hard to find silicon for non-conforming use cases, non-typical use cases, and it's hard to develop the IP and architectural knowledge coming forward, next generation, and historical, to be able to handle and accommodate all these cases. And so ideally, there would be a bridge that can do all these things, and it is a little bit more flexible. And so, the idea of a programmable bridge, one that you could program in capabilities to, and really just has the interfaces you need, and leverages programmability in the device to do whatever you want to do, would be kind of the nirvana. And it would cover all of these cases that we discussed at the beginning, the common bridging use cases. Image sensor to application processor mismatch, processor to display mismatch, aggregation, and multiplexing. And this really is not, I'm talking about image sensors and displays here today, but this is a bridging, this goes across all borders of audio to sensor fusion to all different cases. So it's really camera and display agnostic, but for the purposes of this, we're focusing there. And so there's always been, FPGAs have always played here. Because for these kind of non-typical use cases, you need that flexibility. but they've never been at the price point of an ASIC and an ASSP. And so the ideal situation is if you can combine the time to market, flexibility, and cost of, time to market and flexibility of FPGA with the cost, power, and size and performance of an ASSP, that is the nirvana. And so this is not an advertisement, but this is kind of this is the only device that's out there like this that is really kind of our vision at Lattice of how we may solve this problem, and we're open to feedback on it. But we just released this device, and it's basically a variety of interfaces, some programmable, some hard interfaces surrounding a programmable FPGA fabric. And it has just enough FPGA fabric, just enough RAM to cover all of the muxing, merging, demux, arbitration, splitting, data conversion that you would probably want to do. So it's kind of balanced. Everything for the number of PHYs and number of interfaces it has with the amount of gates that you would need. And so the problems are, even with this, you must have the right amount of interfaces and types of interfaces. This is what we struggle on. And you must have the right amount of programmability to cover most use cases. Second problem is that architectural knowledge and the historical and future-looking knowledge surrounding these interfaces and use cases. So you need to have the right IPs to cover the most common use cases, and then you can spin off other capabilities after that. So one way to solve the problem is to kind of have a utility or a tool that you can say, I want these interfaces in, I want these interfaces out, this is my input speed, this is my output speed, generate that bridge. And you could generate that bridge. And so here's some of the examples of common use cases that may be covered as you would develop such of a architectural platform. Okay, third problem is it must have the right form factor. So it's gotta be in the same form factor as an ASSP or an ASIC. So we're talking about, wafer level packaging, BGA packaging, and it also needs to accommodate needs for industrial and automotive. So maybe some larger pitch packages or some industrial solutions that may do 2-layer or 4-layer boards. So you can't pay a penalty for using programmable logic if you want to be in volume systems. Okay, so this slide is how can you do this? No one's really been able to kind of crack this code of having a device that's the same price, power, and performance as an ASIC, but gives you the programmability of an FPGA. And so it really comes down to how you approach the use cases and the paradigm. So an ASSP, once you design it, it's done. That's the use cases that you can do. And so commonly what occurs is you take a subset. You take, I'm going to do raw and I'm going to do YUV. And maybe I'll do some RGB. And I'm going to do 8 bits per pixel, 10 bits per pixel, and 12 bits per pixel. I'm going to do 1 lane, 2 lane, and 4 lane. And I'm going to cover continuous and non-continuous clocking modes. The difference in this approach is that it's based on firmware loads. So there's a trade-off between approaching the problem from most customers are never going to use in their system raw and YUV at the same time. So why does the customer on an ASSP have to pay the penalty of supporting both? If you go by firmware loads, you can make a custom firmware for that particular situation. So I'm going to only cover YUV, 8 bits per pixel, and 1 lane per that firmware. I'm going to load it into the device. So this is a smaller amount of code, or a smaller amount of gates than this design, And so I can offset the penalty of FPGA fabric being larger, taking up more gates, by doing a simplified design and having different firmware loads. So if I go through these kind of the considerations that we've talked about, time to market, FPGA wins. You can develop and design in real time. That's, great. So you want that. Small form factor, wafer level chip scale and flip chip packages. So same package, and the way to offset that is customized firmware per the use case, and so you're using an equivalent amount of gates to accomplish the same problem and handling unique capabilities, one firmware at a time. Same behavior. So actually, this programmable ASSP concept has the capabilities of an ASSP, but then also has different ways to configure. So you may want to configure from the AP. You may want to have different firmware loads at different times, so you need a fast load time, and you need to be able to store the firmware in the AP. You may want to boot from an external SPI flash, very similar to traditional FPGA, but then also you want some sort of non-volatile memory. And so like an eFuse technology where you can, generate your IP, put it in the device, do your prototyping, and once you're done and you're ready to go to production, you burn some eFuses, that device becomes an ASIC at that point. That would be very advantageous. And one way to resolve some of the FPGA versus ASSP problems. Same low power, so again, optimized use cases. You offset the FPGA gates with custom use cases, focused use cases with firmware loads. Very similar to kind of like MCU type mentality. And then same low cost, so again, you got to be pad limited, not gate limited, and that kind of goes with the wafer level packages and that stuff. Okay, so future considerations. Main thing I wanted to say here, and I guess I didn't really cover it, is that as ecosystem standards, what we noticed when CSI2 and MIPI DSI became popular, we did one design, which was CSI2 to CMOS. And shortly after we did that design, we had all these permutations of use cases coming out. And before that time, we thought, oh no, there's a standardization occurring around image sensors, and we've been doing proprietary bridges for a long time. All of that business is going to go away. And it was actually the opposite. We had way more business as a result of standardization because it started to reduce the cost, power, and size of the devices, and that enabled this mobile-influenced next generation ecosystem. So ecosystem standards enable innovation in a variety of ways. And because it brings down the cost, brings down the power, brings down the size, and brings commonality to use cases, which invokes new ones. FPGA programmability enables standardization and adoption, so it reduces the risk of needing to be backwards compatible. You can feel comfortable going to the next latest and greatest thing if you have a programmable solution sitting by. FPGA programmability is inexpensive, so with the right architecture, it can be the same as ASSP. And then this is just a last comment, so help FPGA programmability help you. So we're only as good as the interfaces that we have, and so we really need, as we try to help the ecosystem, we really need feedback on the next generation solutions and the things that you want us to see. So, please talk to me after the presentation or today or tomorrow. I've heard all the use cases. The craziest use case I ever heard was somebody wanted to develop a fishing lure with a CSI2 camera on it. And so they needed a bridge for that. So I've heard them all. Happy to talk to you about any idea. It won't surprise me. Just come talk to me. And that's what we really need in order to have the things in advance for you so that when you go to the next latest and greatest things, you can feel comfortable about doing it. I think that's it for me.
Thank you.
Thanks for letting me speak, and let me know if you have any questions.
Yeah. Any questions for Grant?
Specifically for the PHYs, do you customize the PHY port on the FPGA, or is that the RTL and you rely on general physical interfaces?
Yeah, so the question is, are these custom interfaces, or are they more flexible and you're handling the interface in the FPGA fabric? It's a combination. So, in some devices, we have hardened PHYs that are kind of off the shelf, meet the standardization requirements, tried and true, proven. And then on the other side, we kind of have our flexible, traditional FPGA IOs with, flexible LVDS, CMOS, dynamic capabilities, and then additional gearing ratios to gear that down to fabric speeds. So it's kind of a not one solution fits all, especially in this kind of programmable ASSP route, because it takes a long time to design those custom IOs. And if you're trying to support a variety of standards with only a handset of IOs doing, one IO can do multiple functions, that takes a lot more time to develop. And so you may want to go to market faster with a hard, does one thing interface, and then the other interface is a little bit more flexible. But we do decide where to partition the architecture such that it leaves flexibility to the user. So for example, like on our DeFi, we have RX and TX. You can do reverse turnaround mode. You can do things that people are in the standards but people aren't using right now or not aggressively. We try to leave it, partition the flexibility such that you can do those next generation cases.
Any other question for Grant?
Cool. Thanks a lot, guys.
Thank you, Grant.